Hey folks, I just wanted to shoot a quick video your way with the three energy types that we're going to be dealing with and sort of a definition for each and how we can tell each energy type is involved in a particular problem type. We got a little rushed with this when we did this in class for some classes, but I think this is just a good thing to have a nice quick overview of and to be able to review pretty quickly. So the three that we're going to deal with in this class anyway are kinetic, gravitational potential, and spring potential energies. So first off, kinetic energy. This is energy that has to do with the motion of an object. So if we have some object that is moving, it has some speed, v, then it has kinetic energy. Larger objects, more massive objects, will have more kinetic energy. And faster objects, objects with higher speeds, will have more kinetic energy as well. Careful when you write your K is here. We do have a lowercase k to represent spring constant. That comes in down here. This one is a capital K, so make sure that, that you're distinguishing between those two. I have to be careful on that because I have sloppy handwriting, so watch yours too. Next up, we've got gravitational potential, and I think this one is probably the trickiest one for people to understand and recognize. Gravitational potential energy is energy that's associated with a system rather than an object individually. And it has to be a system where we have two different pieces, at a minimum, two different pieces, that have a gravitational force trying to pull them back together, and they're separated by some distance. So the idea is that these objects, because of gravity, they have the potential to fall back toward each other. Most often, we'll see gravitational potential as potential energy between the Earth as one object and then some other object that has been raised above the surface of the Earth and it has the potential to fall back down. So if we think about, say, dropping a ball from up high, when we get it up high, we're giving it the potential to fall downward. Gravitational potential energy is often associated with objects that are going to be falling downward. So while it's up high, while it's above what we call the reference level, which is just where we decide zero energy is going to be, it has gravitational potential energy. And the amount of gravitational potential energy it has will be the mass of the object times the acceleration due to gravity times the delta y, which is just the height above, or it could be the height below the that reference level that we set. More often than not, we'll say that an object, if an object is on the ground, then the object and the Earth together are going to have zero gravitational potential energy. We get to define that though, so maybe I'm not dropping an object and it's going to hit the ground, maybe I'm dropping an object and it's going to hit, say, a table. In that case, it might make more sense then to say that we're going to have zero gravitational potential energy when the ball is at the table instead of on the ground, just to give us a zero to throw into our number somewhere. Throw into our calculation somewhere rather. More generally, gravitational potential energy can be solved for using this equation, the capital G, m1, m2 over r. The only time we need to use this equation is when we're looking at really big distances between the objects, in particular distances where this value for gravitational field strength would not be constant. So if we wanted to look at, say, the gravitational potential energy and how it changes when we send a rocket ship from the ground all the way up into orbit, a really significant distance away, where g is no longer going to be 9.8 meters per second squared up there, that's where we would want to use this. And then oddly, I forgot to put this in here, oddly at first, and it seems odd anyway, this also has a negative sign with it. So the negative is always going to be present in this energy type. Gravitational potential energy by this standard will always be a negative value. And as we get our objects farther and farther and farther away, so r gets larger and larger and larger, we're going to get a number that's closer and closer to zero. So when the objects are far away, we have some very small negative number. When they're closer together, we have a larger negative number, which means that as they get closer together, we get closer to the, we get to smaller values or lower values of energy, which is the same thing we have with this setup. As we have our, say, our ball falling, we get to lower values of gravitational potential energy. We just call it positive usually there, instead of lower values in the negative region. So a little bit tricky to work with those. You may have seen this before as m times g times h, mass times gravity times height. So that's a good way to think of it as well. Last up, we have spring potential energy. This is energy associated with a stretched or compressed spring. So as we stretch a spring, we have to apply some force to it over some distance to make it stretch. So we have to do work on the spring, which means we give it energy. That spring then has the potential to snap back together, or if we compress it, it has the potential to spring back apart. The amount of spring potential energy here is 1/2 times K, the spring constant, so lowercase k for spring constant, not the capital K for kinetic energy here, but lowercase k for spring constant, times x, where x is how far, it's a distance, how far we've stretched or compressed that spring from its resting length. So if our spring is normally this long and we stretch it out so it's 10 centimeters longer than usual, we use 10 centimeters or 0.1 meters for x here. And same thing here. If it's usually, same thing for a compression. If it's usually this long and we compress it by 10 centimeters, we'd still use 0.1 meters or 10 centimeters for that value for x. The k value, remember, is a ratio of force to distance for that thing. So the other equation that might get used on these problems frequently, though it isn't an energy type, is Hooke's law, which says that the magnitude of the spring force is equal to the spring constant times the magnitude of the distance that's been stretched or compressed. So if we try and isolate K here, it'd just be force divided by distance stretched or compressed. So the idea is if we have a 500 Newton per meter spring constant, that means it takes 500 newtons of force to stretch it out by 1 meter. And we have this linear relationship, so if we only want to stretch it out 1/2 meter, then it would take half as much force, so 250 newtons of force. So spring constant K we often calculate using this equation called Hooke's law, and then we can plug that into this equation for spring energy if need be. Just be careful here that we are using energies when we're asked to use energies. People will often calculate a force using Hooke's law when a problem asks you for spring energy instead of spring force. So just something else to watch for. The same thing can happen up here. If they ask you about a gravitational energy, gravitational potential energy, be sure you're not giving them the gravitational force or the gravitational acceleration. There's a lot of gravitationals out there, so got to keep them straight. The U's both go with potential energy. And in general, we say potential energy is associated with the relative positions of parts of a system. So we have to have some force between the parts of the system, and we have to have some significant positioning of those parts of the system. For the spring, that definition works if you remember that a spring is not really just a spring, but a collection of atoms that want to be in a certain orientation. And if we change the orientation or change the arrangement of those atoms, they want to spring back to their original arrangement. So we kind of have to think of it that way for the definition for potential to make sense. Otherwise, we get the idea that the potential energy is energy associated with a single object, which doesn't really fit with our other definition for potential. So these are both energies for systems, a spring system, and then some system of multiple objects with gravity between them. Kinetic energy can be energy for a whole system, but more often it's energy associated with a single object within that system. So then we put all these equations into those conservation of energy type equations. We just have to be able to recognize, when is it that kinetic energy is changing, and we ought to think about it. When is it that gravitational potential energy is changing, and we ought to think about it. When is it that spring potential energy is changing, and we ought to think about it. So hopefully these definitions and equations will help clarify that for you. Thanks very much. If you learned something from this video, I'd encourage you to like it or share it, and if you think future videos might help you out, then subscribe as well. Take care.